In this lesson, we're going to go through an entire chapter of electrochemistry. We'll start off with a little refresher on how to determine oxidation states. We'll balance oxidation-reduction reactions. We will go through how you identify who's oxidized, who's reduced, who's the reducing agent, who's the oxidizing agent, some pesky little things. We'll talk about galvanic versus electrolytic cells. We'll calculate both standard and non-standard cell potentials. And finally, we'll finish off the discussion with some of those pesky electrolysis calculations. You might take this moment to just hit the subscribe button ever so quickly if you want to be notified as I release more of these. And if you're looking for practice problems and cheat sheets and such, check out chadsprep.com. My ultimate general chemistry course has over 1,200 practice questions and counting. All right, to introduce the topic of electrochemistry, we've got to remind ourselves of what an oxidation-reduction reaction is. So oxidation-reduction reaction is just simply a transfer of electrons. One species is losing the electrons and is giving them away to the species that is gaining the electrons. Now we've got a couple of mnemonics here to remind us of what the definitions of oxidation and reduction are. So we've got Leo the lion says grrr, which is much more fun to say than oil rig. Or, I mean, if you try to say it oil rig, it just sounds dumb. So, but Leo the lion says grr here. So lose electrons oxidation, gain electrons reduction. So or oil rig is real common as well. So oxidation is loss, reduction is gain. You have to remember that it's the loss and gain of electrons. Now, one thing to note about this, so if you gain money, then your bank account goes up. And if you lose money, your bank account goes down. But when you gain and lose electrons, it works the opposite way as far as your oxidation state goes. So when you gain electrons, they're negatively charged. And because you're gaining negative charges, your oxidation state goes down. And that's why they call gaining electrons getting reduced. So if your oxidation state goes down, yeah, you gained electrons, you got reduced. If your oxidation state goes up, then you lost electrons and you got oxidized. So it's going to seem a little backwards that when you gain something, electrons in this case, that you get reduced, but that's exactly how it works. So hopefully that kind of helps you keep it straight here. So the hallmark of an oxidation-reduction reaction is that oxidation states change. So we have to give ourselves a little reminder of how we calculate oxidation states. And in fact, I might give you some slightly different rules than maybe the ones you're presented with in your first semester of general chemistry here. So I've got 6 lovely rules I break it up into, and you just want to follow them in order till you get to rule 6. So rule number 1 is the most important, and rule number 1 just simply says that any element in its elemental form has a 0 oxidation state. Okay. So if you look at the way this works, so this includes like diatomics and things of this sort, not just monatomics, but if you have any element all by itself and there's no charge written, well then it must be in the 0 oxidation state, even if it's a diatomic and stuff. So if we look at like chlorine and oxygen, which are diatomics, well, it's still just one element all by itself and there's no charge listed, and if it had a charge, we'd have to write it. So these must be in the 0 oxidation state. Same thing for ozone. There's some random triatomics here, but again, if there's no charge, then all 3 oxygens must all be in that 0 oxidation state. So that's rule number 1, and most of the time we're dealing with compounds, and very rarely are you ever going to have something in a compound with a 0 oxidation state. And so usually we'll skip rule number 1 once we recognize we have a compound. So if you look at the rest of these examples we're going to do, they're all compounds made of multiple elements, and so you just move on past rule number 1 and go straight to rule number 2. And if you look for rule number 2, the first thing you want to look for are group 1 and group 2 metals, because in ionic compounds, group 1 metals are always +1 and group 2 metals are always +2. Now notice I said in ionic compounds. So notice group 1 and group 2 metals aren't always +1 and +2 because they're not when they're in the elemental form. But if they're in a compound, an ionic compound, they're going to be +1 and +2 respectively every time. So if we look at magnesium chloride here, so magnesium is in group 2 on the periodic table, and as part of a compound is always going to be +2. Cool, so that's the first thing I assign. So, and once you've got one element left that you haven't assigned, you just skip straight down to rule number 6. And the last element unassigned has to balance out the compound. Now, if it's a compound, which will be neutral overall, then you balance it out to 0. So, but if it's an ion, then you'll just balance it out to whatever the ion's total charge is. So, but in this case, it is a neutral compound, so we'll just balance it out to 0. And for this to work, those 2 chlorines each have to be -1. So there's 2 of them, -1 each, for a total of -2. That way +2 and -2 adds up to 0. Now another way you could look at this is we could have just said from the get-go, let's do this in blue to distinguish, we could have said whatever magnesium is +2 times whatever chlorine is has to add up to 0. And we could have made a little algebra equation out of this, and we would have put +2 in for magnesium, and then we would have solved for chloride and still got -1 the same way. So, but you can turn every one of these into an algebra equation, if you will. You just got to know who do you assign first and things of the sort. So there's magnesium chloride. So if we move on to the next one here, we've got N2O4. So rule number 1 deals with things in their elemental form. This is a compound. We'll skip it. Rule number 2 deals with group 1 and group 2 metals. We don't have any group 1 or group 2 metals. Rule number 3 deals with hydrogen. Hydrogen will be the next thing to assign. I don't have any hydrogen. Okay, moving on. So rule number 4 deals with transition metals. I don't have any transition metals, so we move on. So finally, rule number 5 says the most electronegative element gets its typical oxidation state. And so in this case, so who's more electronegative? Nitrogen and oxygen. And you're supposed to remember that fluorine's the most electronegative. And as you go up and to the right of the periodic table, you get more electronegative. And so oxygen's more electronegative. And oxygen's typical oxidation state is -2. And what I mean by typical oxidation state here is based on its placement on the periodic table, what kind of charge does it normally take as an either cation or anion to get a filled octet? And for oxygen with 6 valence electrons, he wants to gain 2 to get that filled octet, which is why his typical charge in this context is going to be -2. Cool, from here we've only got one element left, and that one element left just has to balance the rest of this out. So in this case we've got 4 oxygens at -2 each. That's a total of -8. So now one thing to note, the oxidation state is -2, but there's a total charge of -8. So note that if somebody were to ask you for the oxidation state, if you said the oxidation state's -8, you'd be wrong, because the oxidation state is already, the oxidation state is always defined per atom. And so per atom, they're -2 each. That's the oxidation state for oxygen. But we do have to balance out the total charge here. So since all of those oxygens are -8, then all of these nitrogens must be +8. And for them to be +8, and there's 2 of them, then each of them are +4. And so nitrogen's oxidation state here is +4, determined by our lovely rules. Let's move on to the next one. So for the next one here, we've again got a compound, so there's nobody in their elemental form. We'll skip right past rule number 1 and look for group 1 and group 2 metals, and we've got a group 1 metal here in sodium, so +1. Great, we still got 3 elements left. We'll move on to rule number 3, and we've got hydrogen. So, and hydrogen is almost always +1 in a compound. So the only time hydrogen is going to be -1 in a compound is if it's an anion with like a metal hydride, just a metal and hydrogen, nothing else. So we do have a metal and hydrogen, but we got other stuff here. So, but if it was just a metal hydride, that's the only time hydrogen ends up being -1. All right, we still got 2 elements left, so we'll keep going down the rules. Rule number 4, transition metals, carbon and oxygen, neither one's a transition metal. Moving on. So the more electronegative element, carbon or oxygen, is going to get its typical charge, and that's oxygen yet again. And so in this case, oxygen is going to be -2, and now we've got 1 element left in carbon. So if we take a look at our total charge here, so we got 3 oxygens for a grand total of -6. So, but we had just the 1 sodium and just the 1 hydrogen. And so we can see that the only carbon we have, for this to all balance out to 0, there's no overall charge, it's a neutral compound, it's going to have to be +4. And in this case, that's just all on 1 carbon, so carbon's oxidation state is simply just +4. Cool. Let's do another example. All right, so here we've got copper sulfate. So I wanted to make sure we did an example with a transition metal here. So if we look at rule number 1, elements in their elemental form, skip. Rule number 2 deals with group 1 and 2 metals, don't have any. Rule number 3 deals with hydrogen, don't have any. So finally, rule number 4 deals with transition metals. And typically a transition metal as a cation is going to have variable charges, right? And you're going to have to figure out what its oxidation state is based on what anion it's with. In this case, it is with sulfate. And you're supposed to remember all those polyatomic ions you memorized in the first semester. And for sulfate, you're supposed to know, oh yeah, sulfate's got a -2 charge, and we have 1 of them. Therefore, the copper over here must be +2. Cool. And indeed, he is +2. So, but we still haven't actually assigned sulfur and oxygen. We just said sulfate as a whole is -2, but we never actually assigned sulfur and oxygen. So in this case, we'll jump right down to rule number 5, and the more electronegative atom, which is oxygen, gets his typical oxidation state -2, and that's 4 oxygens for a total of -8. We got the 1 copper for a total of +2, and we can see over here that to make this balance out to 0, again, this is a neutral compound, sulfur here is going to need to be +6, and there's just 1 of them, so it's all +6, all on that 1 sulfur. Cool, and that's how this works. The other thing you could have done here with polyatomic ions, you could actually pull that polyatomic ion out of the compound. Nothing says you can't. So, and do it from here. And instead of balancing out to 0 now, we'd be balancing it out to a total of -2. Now, in this case, we just go do the same process and say oxygen's -2. There's 4 of them for a total of -8. And in this case, what do I add to -8 to get a total of -2? So we're not balancing it out to 0 anymore. And we realize that sulfur would have had to been +6. And so whether we figured it out in the context of the entire compound or pulled it out and figured it out that way, works either way. So it wasn't a big deal here, but sometimes when you've got multiple polyatomic ions, it's sometimes easier just to pull one out and evaluate one than to look at several in the context of one compound. There's just more opportunities to make some algebra error. All right, moving on to H2O2. This is hydrogen peroxide. And so first semester, we often teach you how to recognize a peroxide and then memorize that when you have a peroxide, oxygen's only -1. So, but with this set of rules, it's just going to naturally fall out that you'll realize that oxygen's -1. So first rule deals with elements in their elemental form. This is a compound. We'll skip it. Rule number 2 deals with group 1 or 2 metals. We've got, hydrogen is in group 1, but he's not a metal. So rule number 2, group 1 and 2 metals don't have any. Rule number 3 deals with hydrogen, and hydrogen's going to be +1. So, and at that point, we've got one element left, so we'll just jump straight down to rule number 6. So when rule number 6 says just the element remaining has to balance out the charge. In this case, that's going to have to make oxygen -1, so to balance out the 2 hydrogens that were +1. So the oxygens are -1 each. And again, that's the hallmark of a peroxide, when oxygen's not in its normal -2 state, but in its -1 state. Cool. And again, we didn't have to memorize how to recognize a peroxide. It just naturally determined that oxygen was -1. Cool, this is potassium superoxide, which is even more unusual. But again, if you follow the rules, figuring out the oxidation state here, it'll just naturally fall into place. All right, so nobody in their elemental form, skip rule number 1. Rule number 2, any group 1 or 2 metals. And in this case, we've got a group 1 metal, potassium, so he's +1. And now with only one element left, oxygen just has to be whatever he has to be to balance this out. And this is where it gets a little unusual. There's 2 oxygens there. They have to have a total of -1 charge, but that -1 charge is spread across 2 oxygens, so they're each going to be -1/2. So not the most common thing to see a fraction for an oxidation state, but the oxidation state is indeed -1/2. And when a compound has oxygen in the -1/2 oxidation state, it's called a superoxide. Not the most common, compound in the world. Not too many of these. If you look here, what's really going on is you have a polyatomic ion that has 2 oxygens in it, and those 2 oxygens are sharing 1 additional electron, so that on average, they're -1/2. Finally, the last one here is going to see another fraction for an oxidation state. This is sodium azide, kind of in a lot of your airbags these days. And in this case, we've got a group 1 metal in sodium, so we'll assign him first, according to rule number 2. And then we've only got 1 element left, so we'll just jump straight back down to rule number 6. So, and in this case, if sodium's +1, then all 3 nitrogens combined must be -1, and that means individually they're each -1/3. And again, another example of a fractional oxidation state for -1/3, but the azide ion, N3- here, so is a polyatomic ion in which 3 nitrogens share 1 extra electron, so that on average, they're each -1/3. So that's how that works. So I just want to make sure you'd seen fractions before. A lot of times the first time a student ever sees a fractional oxidation state is on a test, and they're like, that doesn't make sense, and they just keep trying to rework it. So, but it is possible. It is not typical, but it is possible, just an FYI. All right, now we've got to balance some oxidation-reduction reactions. We'll call them redox reactions for short. And this is a pain in the butt. This is a more involved process than balancing all the other chemical reactions you've balanced up to this point. And there is a discrete set of rules you need to follow to kind of get this. And to get those rules down pat, you really just need to work several examples. We're going to work 2 of them here. So, and we'll see how complicated this is. But we'll give you a pretty concrete set of rules so you can kind of just follow the pattern. But you do got to get these rules down. Now, there's more than one way to learn this. I'm going to teach what's called the half reaction method, which is probably the less error-prone method for incoming chemistry students and stuff. So, the first one we're going to do here is H2O2 plus PBS going to PbSO4 plus water. So, and what we want to do is split this into 2 half reactions, where one of them is the oxidation half reaction, one of them is the reduction half reaction. So, and if we look at some oxidation states here, so some of these we already assigned, we can see that oxygen here is going from -1 on this side to -2 on the other side. That's going to be a reduction. It's going from -1 down to -2. That's reduction. So that's got to be in one of our half reactions. So, and then we can take a look over here at lead sulfide, and lead here is +2, sulfur is -2. Here lead is still +2, that hasn't changed, but sulfur is now +6. And so with sulfur going from -2 up to +6, that's getting higher. He's losing electrons and he's being oxidized. That'll be our other half reaction. And so in this case, we're going to have one half reaction where H2O2 goes to water, and then we'll have another one where PBS goes to PbSO4. So first step, find who's getting oxidized, find who's getting reduced, and split it up into separate half reactions. One oxidation half, one reduction half. All right. So from there, you're going to find out that all these lovely oxidation reduction reactions are aqueous reactions, and we're always going to balance out oxygens with water molecules and hydrogens with H+ ions. So, and we can just add them as we need because they're in an aqueous solution. In this case, though, we need to, because they're so ubiquitous and stuff like that, we're always going to add them last. We'll always do oxygens second to last by adding water molecules, and then adding hydrogens dead last with H+ ions. And the idea is that when you add the water molecules, you're going to incorporate some more hydrogens as well. So you got to add the hydrogens very last. So before you do the oxygens and hydrogens, then you got to make sure that everything else is balanced first. And you want to start with who's being oxidized or reduced. So in the first case, we said that it was oxygen already being oxidized or reduced, and there's only hydrogen and oxygen in this one. So the first step here is not really necessary in the first half reaction, but in the second one, you want to make sure that everything besides oxygen and hydrogen is balanced. Well, in this case, the leads are balanced, the sulfurs are balanced, and it was the sulfur that was key here because he's the one that's changing oxidation states. They're already balanced, and so this rule is not needed in this example. So after that, you want to make sure the oxygens are balanced by adding water molecules. Well, in the top one, I've got two oxygens on the left, only one on the right. I would need to add another water molecule. Well, instead of putting plus water, I'm just going to put a coefficient of 2 in front of this half reaction. Cool. Now for the other one, I've got no oxygens on the left. I've got 4 on the right. So I'm going to have to add water molecules on this side, and I'm going to need to add 4 of them. Cool. And now the oxygens are balanced in both half reactions. And so finally, we'll balance the hydrogens by adding H+ ions. In the first one, we've got 2 hydrogen atoms on the left. We've got 4 of them on the right. So I'm going to need 2 more over here. So I'll add 2 H+. For the second one here, I've got 8 hydrogen atoms on the left. I've got none on the right. So I'm going to need to add 8 hydrogen atoms on the right, 8 H+. Cool. Last step to balancing the half reactions is to balance out the charge. And you balance out the charge by adding electrons. So there's a couple different ways you could look at this. You could look at the change in oxidation states. Like here I'm looking at, well, oxygen's -1, he's going to -2, but how many are doing that? And you could figure out how many electrons are needed. So, or you could just balance out the overall charge. So if you look, so for the reactant side of this first one, hydrogen peroxide has no overall charge, but I've got 2 H+, and so the entire side of the reaction here is +2, whereas water's a neutral molecule, so this side of the reaction has a charge of 0. And so if you're adding electrons which are negative, you're just going to add them to whichever side is more positive till the charges are equal. And so in this case, this is the more positive side on the reactant side. And so we need to add 2 electrons. Now both sides have a total charge of 0, and it's balanced. Now, one thing you should note, when electrons are a reactant, that's when they're being gained, and the top reaction is the reduction. And again, we already knew that because we knew oxygen was going from, again, -1 to -2. His oxidation state's going down. It's getting more negative in this case. All right, in the second one here, so both the reactants are neutral molecules, and so the total charge here on the reactant side is 0. On the product side, PbSO4 is a neutral molecule, but there's 8 H+, and so the total charge is +8. And so in this case, it's the product side that's more positive. How many more positive is it? Well, it's more positive by 8, so I'm going to need to add 8 electrons. And now both sides of this half reaction are now balanced as well. Okay. So now the last step here before we combine these is that the electrons that are being gained here and the electrons that are being lost here are the same electrons. It's really just this, second electron is transferring the electrons it loses to the first one who gains it. And since they're the same electrons, those numbers have to match. And so in this case, what you want to find is what's called the least common multiple. You might remember that from back in the day. So the least common multiple between 2 electrons and 8 electrons, what number do they both divide into evenly? Well, they both go into 8 evenly as the least common multiple. And this one's already an 8 electron process, but the first one, to make it an 8 electron process, I'm going to multiply the whole thing times 4. That multiplies every single coefficient by 4. So that way they're both an 8-electron process. And once we've done that, and you can write it out, or you can just kind of envision it in your head, which is what I'm going to do, then you're ready to combine these two half reactions back into a whole reaction. And so in this case, 4 times 2 would be 8 electrons. 4 times 2 would be 8H plus. 4 times 1 would be plus 4H2O2. Cool, and that's all the reactants from the first one. Now I'll add in all the reactants from the second one. And this one we're using it as is, so we'll just add in 4 waters. Let's try that again. Plus PBS, and then we'll do all the products as well. And so again, from the first one, we've got 4 times 2 is 8 waters. So and again, we're using this one as it is, so plus PbSO4 plus 8H plus 8 electrons. And if you've done this correctly, the electrons should cancel. So anything that's in common on both sides should cancel. And so those electrons definitely gone. So, and if you've balanced it properly up to this step, they should always cancel out. So in a half reaction, you're going to have electrons, but in any properly balanced complete reaction, there should never be any electrons. They've already should have canceled out of the process here. So from here, again, anything that shows up on both sides, you're going to want to cancel as well. And especially you want to look for water and H plus because we use them to balance half reactions so commonly. So they often show up in both, and you're going to have some canceling going on. And so in this case, these 8H plus are going to cancel out these 8H plus, so those cancel out completely. So, and then here we got 4 waters on this side, 8 on this side, so these 4 waters are gone completely. And they cancel out 4 out of the 8 here to leave us with 4 left. Cool, and then we'll write this one more time. So now we've got 4H2O2 plus PBS. Going to 4 waters plus PbSO4. And that is our complete balanced reaction. Cool. So one thing to note, we don't have any H plus in this reaction whatsoever. And it turns out when you've got H plus somewhere showing up in your reaction, so oftentimes they can say balance it in acidic conditions or balance it in basic conditions. And there's a difference in, you've got a finishing step if you want to balance it in base. Because we always balance hydrogens with H plus, by default, we're always balancing an acid. And so if they ask you to balance it in base, we'd actually have an extra step to do. But in this example, if there's no H plus in the net reaction, then this is the balanced reaction in both acid and base. So, and then the idea is that, you know, with redox reactions, so their cell potentials are totally pH dependent. If you do them at a low pH under acidic conditions or a high pH under basic conditions, it's totally going to change that cell potential. And so that's why we talk about balancing them in acid or base. But with this one, with no H plus in the net reaction, it is no different either way. But we'll see a difference in the next example. All right, in this next example, so first thing was we want to identify who's changing oxidation states. And manganese here is actually in the +7 oxidation state if you work it out in permanganate, going to +2. So to go from +7 down to +2, that's getting reduced. So iodine, on the other hand, starts out as -1 and ends up in the elemental form in the 0 oxidation state. So going from -1 up to 0, so that's going to be getting oxidized. That's losing electrons. So we'll split that in half here for a second. All right, now we've got our 2 half reactions. One thing I want to point out is oftentimes, you know, we can do it from here, we can do it from the entire balanced reaction, but we've already identified who actually is getting oxidized and who's getting reduced and stuff like this. And so if you look here, it was permanganate, so, or manganese that was getting reduced. So going from +7 to +2. And if you want to say that manganese is the element getting reduced, fantastic. Or if you want to say the entire permanganate MnO4- ion is getting reduced, fantastic. Either one of those is acceptable. Now on the other side, we've got iodine again going from -1 up to the 0 oxidation state. So he is getting oxidized. Cool, and whether you want to say that iodine is getting oxidized or it's that the iodide ion is getting oxidized, either one of those is acceptable. Hopefully you've realized that when we talk about who's getting oxidized and who's getting reduced, it's always the reactants that are getting oxidized or reduced, not the products. So Again, if you wanted to say that, either manganese is the element or MnO4 minus is the entire species that's getting reduced, that's totally good. But if you said that Mn2 plus is getting reduced, that'd be totally wrong. It's never the product. It's always the reactant. Now, we've also got to talk about the agents here, and this is going to seem a little bit backwards, but in this case, since MnO4 minus is getting reduced, it makes him, turns out, the oxidizing agent, which is sometimes called the oxidant. So, and it's always on the reactant side. So, and it always seems backwards. Who gets reduced is the oxidizing agent. We'll see it the other way around too. So here it's I minus that's getting oxidized. That makes him the reducing agent or reductant as well. So when you're identifying your oxidizing and reducing agents, they're always going to be on the reactant side, but there is one major difference. So whereas we could say that either Mn or MnO4 minus is getting reduced, when you talk about the agent, you have to give the entire chemical species. So if you said right now that Mn was the oxidant, that would be totally wrong. It's MnO4 minus that is the oxidant, the entire chemical species on the reactant side. Same thing here, it's I minus that is the reductant. All right, now this seems backwards, so let's just pretend for a minute you're like, Chad, this is so confusing, and you decide to jump through the screen here and punch me in the face. Cool? So my question for you is, who got punched? Well, I did. But who did the punching? You did. So, and almost always works out this way, that the person doing the punching and the person who gets punched are not the same person. I mean, I guess we can envision a situation where it could be, but not usually, right? So same thing here. So the species that's getting reduced is not the species that's doing the reducing. So he's getting reduced here, MnO4 minus, but it's the other species that's causing him to get reduced that's doing the reducing. We might actually say that I minus is reducing MnO4 minus. In the same sense, it's I minus that is getting oxidized, and we might say that it's MnO4 minus that is oxidizing him. And so this is kind of why the terminology is what it is, but at the end of the day, you have to know that the oxidizing agent is the one getting reduced, and the reducing agent is the one getting oxidized, and they're always on the reactant side of the equation. All right, let's get back into balancing this here. So we've got our half reactions. And in this case, you want to make sure that all elements besides oxygen and hydrogen are balanced. And for the first one, that's already true. The manganeses are balanced. For the second one, though, I'm going to need to put a 2 right here. And that's a step a lot of students often forget on this kind of an example. So now we'll want to go and balance the oxygens and hydrogens. Oxygens first. And for the first one, I'll need 4 waters on the product side to balance out the oxygens that were over here. And in the second one, there's no need for oxygens at all. There's no oxygens in the entire half reaction. So no waters to add. Now we'll go balance out the hydrogens. And for the first one, I've got 8 hydrogen atoms on the right-hand side. So I will need to add 8 H plus on the left-hand side. And again, for the second one, we don't have any H pluses to add because hydrogen doesn't show up in this half reaction at all. And finally, now that all the elements are balanced out, now we can go back and add the electrons to balance out the charge. So for the first one here, if we kind of take a look here, so we have 8 plus 1s and then 1 minus 1 for a total of plus 7. And on the product side, the waters are all neutral, but we have 1 manganese ion here that is a total of plus 2. And so in this case, we're going from plus 7 to plus 2. The more positive side gets the electrons, but it's not 7 electrons. It's only the number of electrons you need till they have the same charge. So in the last example, it did balance out to 0, but in this case, I'm going to want to balance them out to both being plus 2. And to do that, we're going to need to add just 5 electrons to that first half reaction. Cool, and now both sides have the same charge, plus 2. Cool, in the second one, the reactant side here, we've got 2 iodide ions, minus 1 each for a total of minus 2. On the product side, elemental iodide is 0. And so the more positive side is the side that's 0. And so we'll add electrons over here, and I'll need to add 2 of them to make the charge balance. And once again, we said when electrons are a reactant, they're being gained, and that's, in this case, reduction. And we said that when electrons are a product, they're being lost, and that is oxidation. Cool, so now we've got our 2 half reactions, but the electrons being lost in the second half reaction are the same as the electrons being gained in the first, but they're definitely not the same number right now. So to combine these, we have to get the least common multiple between 2 and 5. And the lowest number that 2 and 5 both divide into is 10. And so for the first half reaction here, I'm going to have to multiply it by 2 to make it a 10 electron process. And again, that doubles every single coefficient. For the second one, though, I'm going to need to multiply the whole half reaction by 5. And again, that multiplies every coefficient by 5. So, and now it would be 10 electrons gained and 10 electrons lost, and it'll balance out. Now we're ready to combine these. All right, so going over here, 2 times 5 is 10 electrons. 2 times 8 is 16 H plus. 2 times 1 is just 2 MnO4 minus. We've got all the reactants from the first one. Let's get the reactants from the second one. So 5 times 2 would be 10 I minus. And now we've got all the reactants from both of them combined. We'll go to the products now. So 2 times 1 would be 2 Mn2 plus. So, and 2 times 4 would be plus 8H2O. And then 5 of these. And then finally 5 times 2 gets us the 10 electrons. And once again, anything that's in common on both sides is going to cancel. So, and for this one, that is simply just the electrons. We'll get rid of those electrons. And so we'll rewrite this one last time here. There's nothing else in common. Only H pluses on this side, only waters on this side. Let's make that look a little prettier. All right. Now, we said earlier that by default, we follow this set of rules and stuff. We by default are balancing a reaction in acid. And the evidence that we've balanced this in acid is that there's H plus in the reaction. And it doesn't really matter if it's on the reactant side or the product side. If there's H plus in the balanced reaction, you've just balanced it in acid. Cool. And this is the balanced reaction in acid. But because it does have H plus showing up, we could also be asked to balance it in base. For this kind of a redox reaction, it wouldn't be enough for them to just say balance this redox reaction. For the last one, that would have worked. But for this one, they've got to be more specific, and they got to say balance it in acid or balance it in base. Otherwise, we don't know which route to go. But if we were asked to balance it in acid, we would be done. And one quick thing to note, you can always kind of double check yourself. In a properly balanced redox reaction, all of the charges should be balanced. So if you notice, we got 16 plus 1s, 2 minus 1s, 10 more minus 1s. So 16 plus 1s and a total of 12 minus 1s leaves us with a total charge of plus 4. And on the other side, we've got 2 plus 2s, and then these are both neutral for a grand total of plus 4. Now, this doesn't guarantee that we've done it correct, but if these numbers didn't match, you'd for sure know you'd done it wrong. All right, so we balance it in acid, so then how do we go from here to balance it in base, if that's the question? So, and the key is H plus doesn't exist in any significant amount in a basic solution, and so you need to neutralize all of it. So in this case, we're going to add, for every H plus, we're going to add an OH minus. And H plus and OH minus combine to form water. And so in this case, they're going to combine to form 16 waters. Now we have a problem, though. This thing was balanced just a second ago. And so if I add 16 OH minuses to just the reactant side, it's not balanced anymore. And so to make this still work, I've also got to add 16 OH minuses on the product side. That way it's still balanced. Now on the reactant side, it combines with the H plus to form water. On the product side, there's no H plus to combine it with. It's just going to stay as OH minus. So let's write this thing out now. Yet one more time. In fact, we'll have one more after that. So we've now got our 16 waters. In fact, they're already there. And then we've got our 2 MnO4 minus, our 10 I minus, 2 Mn2 plus, 8 waters, 5 I2s, and I'll make sure we don't forget those 16 OH minuses. Just carried it down. All right, because you just formed a bunch of waters, and water shows up so commonly in redox reactions, there's a good chance you got waters on both sides, and you want to make sure you look for that to see if they cancel, and indeed they do. We've got 8 waters on this side. We've got 16 on this side, and so those 8 over there cancel out 8 that were here to leave us with 8 left, and that's why we're going to write this yet one more time. So waters are gone. Cool, and this is the balanced reaction in base. Cool, and the evidence that we've balanced it in base is that there's hydroxide present in the balanced reaction. Cool, so two possible answers to this question. If you're asked to balance in an acid, go with the one circled in red here. If you're asked to balance it in base, go with the one circled in blue instead. All right, now we're going to have a lengthy discussion about electrochemical cells, and there's two main types. We've got galvanic cells, which are also called voltaic cells, and then we've got electrolytic cells. Now, we'll start by having a little more discussion about galvanic cells in this chapter, and we'll finish the chapter up by talking about electrolytic cells. But before we do either, we're just going to quickly compare and contrast them so you know the big difference. And so, biggest difference you can look at is that for a galvanic cell, we have a spontaneous reaction, and we're going to use that spontaneous reaction to produce electricity. So notice this, think about hydroelectric power for a minute. So water naturally falls downhill, it doesn't fall uphill, so to speak, it falls downhill. And we use that spontaneous process of water falling downhill to make electricity. Well, here we're going to use a spontaneous chemical reaction that happens all on its own, it's spontaneous, to make electricity, so to speak, as well. Now, an electrolytic cell, on the other hand, is non-spontaneous. So, and instead of making electricity, it's not a really great description, but I'm going to run with it. So an electrolytic cell is actually going to consume electricity. Cool, and the idea is that an electrolytic cell, it's not, going to make electricity at all, it's going to use it up. So, but we're going to force a non-spontaneous reaction to happen, and a non-spontaneous reaction needs an input of energy to happen, and the way we're going to input that energy is through electricity. And so these use up electricity, these produce electricity. So when you think of a galvanic or voltaic cell, you should be thinking of a battery that produces energy. Now, technically, an electrolytic cell, if you're recharging your battery, so you're actually running your battery exactly backwards. In the forward direction, it's a galvanic cell. But when you're recharging it, it's actually acting as an electrolytic cell. When you're recharging it, it's not a spontaneous reaction. The backwards reaction is not spontaneous, and you toss electricity to recharge your battery. So keep that in mind. But when we talk about electrolytic cells, we'll much more commonly talk about something other than recharging your battery, but we'll get to that a little bit later down the road. Now, a couple things. We got a little bit more definition here, and we got to talk about what's called the anode and what's called the cathode. So, and focus on anode, cathode. In fact, why don't we make that a capital C to match? So, and it turns out these have set definitions. So, the anode is the site where oxidation takes place. It's the electrode where oxidation takes place. And the cathode is the electrode or site where reduction takes place. So, when we can talk about an-ox or red cat for some people. So, but for me, again, I like to think that anode is the site of oxidation. Anode and oxidation both begin with a vowel sound. So, whereas cathode is where reduction takes place, and I like to think of cathode and reduction as both beginning with a consonant. Great. So, at the end of the day, you got to know that the anode is the site where oxidation takes place, period. So, and cathode is the site where reduction takes place, period. It's going to be true in both galvanic cells and electrolytic cells. No difference. So, if you notice, anode's where oxidation takes place, that's where electrons are being lost. Cathode is where reduction takes place, it's where electrons are being gained. And it turns out your anode is going to be connected to your cathode by a wire. And electrons are going to travel through that wire from the anode to the cathode. So we're losing them again at the anode, gaining them at the cathode. So the electrons have to be going from anode to cathode. All right, in your electrolytic cell, there is no difference in that so far. We're still going to have the anode and cathode connected by a wire, and electrons are still going to have to travel from anode to cathode. Now, what's going to be different here is that, again, we said this is a spontaneous process, and this is not a spontaneous process. And so the idea is that the anode and cathode have potentials associated with them. So, and for an anode in a galvanic cell, that potential is negative, whereas the cathode's potential is positive. And so, and potential is not exactly the same thing as charge, but we're going to kind of run with it here. And so electrons being negatively charged are repelled from the anode and attracted to the cathode. And so the electrons are going exactly where they would want to go because it's spontaneous. So, but this is going to be backwards. This is one of the big differences here, is that now the anode is positive and the cathode is negative. And again, this actually means about potential. What this really means is that the anode's at higher potential, the cathode's at lower potential. And there's a relationship between potential and potential energy that you'll talk about in a physics class, and we'll address it in just a second. But if you think of it as charge for a second, you can see that the electrons actually want to go away from the cathode and toward the anode. That's where they want to go, but we want to do this the non-spontaneous direction here. And so naturally the electrons, if you just let them go, they're going this way. And so what do we do to make them go the other way? We connect our wire here to a power source. So you have to hook up your electrolytic cell to like a battery or plug it into the wall or something like that. You have to hook it up to a power source because you're forcing the electrons to go the opposite direction of where they would spontaneously go. You're forcing a non-spontaneous reaction to happen with the input of electricity here. All right. So again, positive and negative is not actually charge. It actually refers to potential. And so at a positive end, you have higher potential. At the negative end, you have lower potential. It's kind of analogous to what you see on your car battery where you have a positive terminal and negative terminal, exactly the same thing. So, but this is where things get a little bit weird because for charges, you have both plus and minus. And it turns out these ideas of potential are related to potential energy, but they defined it relative for a positive charge. And then it just had to be the opposite for a negative charge. So what I mean here is that if we were talking about the movement of protons, for instance, well, with a higher potential, protons have more potential energy. And with a lower potential, protons would have less potential energy. So, but it's the opposite for negative charges. And so for an electron, so here we have higher potential, but for an electron, that actually means lower potential energy. And here we have lower potential, but for an electron being negative, again, that means higher potential energy. And so our electrons here are going from lower potential energy to higher potential energy, which is not the way things normally work, right? When your marker falls, when I drop it, it's going from higher potential energy to lower potential energy. And that's where the way things move spontaneously. And so here we're forcing them to move the non-spontaneous direction with the input of energy. So, but if you look in our spontaneous reaction for the galvanic cell, again, where we have a lower potential, that means electrons have a higher potential energy. And where we have a higher potential, that means electrons have a lower potential energy. And our electrons are going from higher potential energy to lower potential energy, just like we'd normally expect. That's the way things spontaneously go, from higher potential energy to lower potential energy. All right, so you should understand this whole plus and minus thing as being potential. You can kind of think of it as analogous to charge. It kind of helps you, reminds you which way the electrons want to go. So, but you should also realize that in a galvanic cell, it's at the anode that the electrons have higher potential energy, and at the cathode, it's lower potential energy. But in the electrolytic cell, they're actually lower potential energy at the anode and higher potential energy at the cathode. All right, we want to talk a little more about galvanic cells here. And we typically, again, are going to take our two half reactions and actually carry them out in separate compartments. So that way the electrons have to get transferred between the anode and cathode. Otherwise, if these were just in the same compartment, the electrons would just be transferred directly, from one to the other. So, but now they have to actually travel through the wire. And as the electrons actually travel through the wire, they get the opportunity to do work. Just like when water flows downhill, it turns a turbine and gets the opportunity to do work. But if these were in the same solution together, so those electrons would never be traveling and never get a chance to really do work. All right, so in a typical diagram like this, it's proper to put the anode on the left, the cathode on the right. The reaction we're going to take a look at is this guy right here, and I've written it as a spontaneous reaction. You'll just have to take my word for it for now, but we'll figure that out later. So one thing you should realize is that metal and metal ions are pretty common in a lot of the reactions we'll look at. Not ubiquitous, but pretty common. So, and you should realize that when you've got metal ions, since we're dealing with aqueous solutions, those are going to be aqueous. But when you're dealing with just pure metals, those are going to be solids, unless on the odd chance you have mercury, which would be a liquid instead. All right, so even if they don't write the phases, as long as we're dealing with just metals and metal ions, you should know what those phases would be in an aqueous solution. All right, so in this case, if we take a look, so copper here is going from +2 down to the 0 oxidation state, so he's getting reduced. So zinc, on the other hand, is going from 0 oxidation state in his elemental form to the +2 oxidation state. It's going up. So he's getting oxidized. And if you guys recall, again, oxidation takes place at the anode. So it's the zinc half reaction that's happening over here. So in this case, we're going to have zinc going to zinc 2+ +2 electrons. All right, so cathode reaction is going to be the copper one, and we'll have copper 2 plus 2 electrons going to copper. Cool. What's convenient about using metal and metal ions is that you're always going to have a metal. And as long as you've got a solid metal, they make really good electrodes. So your electrodes are going to be suspended in solutions here. So in this case, the electrode on the left is going to just be made out of pure zinc. And the electrode on the right is going to be made out of pure solid copper. And so when you're looking for your identity of your electrode, it doesn't really matter if it's a reactant or a product, but it has to be electrically conductive. And for a lot of half reactions, you're going to have a metal, on one side or the other in its solid state. And so as long as you've got a metal in a solid state, that's typically what your electrode will be made out of. So however, if you've got a half reaction where there's no metal in its solid state present, we have to use what's called an inert electron. And platinum's a pretty common example of an inert electrode. And we call it an inert electrode because it doesn't actually take part in the reaction at all. It's just a way of delivering electrons. Cool. So just want to make that specific here. So also in our aqueous solutions that these electrodes are suspended in, that's where our ions are going to be. So here we've got zinc 2 plus, and in this one we're going to have copper 2 plus. Cool, and we kind of want to map out how this reaction actually happens. So if we look, we got zinc turning into zinc 2 plus. And so in this case, your zinc metal is actually turning into zinc 2 plus in the solution. And so over time, the size of your electrode here is going to get smaller and smaller and smaller. So in here, you're going to get more and more zinc 2 plus ions in the solution. So, but oftentimes we like to focus on the fact that our electrode itself is the reactant. It's being used up. And so the electrode itself is going to lose mass. And so in this example, the anode is losing mass over time. Cool, if we look at the other side though, so here copper, which is what our electrode is made out of, the copper metal is our product. So we're going to be producing more of it. So what actually happens is when the zinc turns into zinc 2 plus, it loses 2 electrons. Those electrons get shipped through the wire, and they sit on the surface of this copper electrode just waiting for a copper ion to bump into it. And when a copper ion bumps into it, it gains those 2 electrons and turns into copper metal. And it turns into copper metal while it's in contact with more copper metal, fusing it to that copper metal. And so this electrode right here is actually going to get a buildup of copper on it over time. And the longer this runs, the more copper buildup you get. And so this electrode over here, so because it's a product in the half reaction, is going to be gaining mass. Cool, and this is pretty common. So for your anode to lose mass and your cathode to gain mass. So however, if we did one of those reactions where an inert electrode was involved, well, inert electrodes don't participate in the reaction. And when you're using an inert electrode, it's not going to gain or lose mass at all. Okay, so we've kind of seen what's going on. So here zinc is losing 2 electrons. It's sending them through the wire. So, and we can see again why they want to go through the wire here. So because our zinc is our anode and it's negative in a galvanic cell, whereas our cathode over here is positive. And so this is the spontaneous direction that electrons want to flow through the wire. But we have one major problem here is we don't have a complete cycle flow of charges, if you will. It's one way to look at it. So like if I take the negative terminal off your car battery, your car doesn't run. So you need the complete flow of electrons around in a full circle in your car. Well, in this case, it's not going to be the complete flow of electrons, but we do need a cyclic flow of charges possible, or you have a dead battery. And as I've written it here, this would be a dead battery. But what we do is we actually connect the solutions here, often with a tube. We'll fill that tube with like maybe some glass beads or some sort of matrix, gel-like matrix, and fill it with a solution of some sort of strong electrolyte. So sodium nitrate's a pretty common strong electrolyte here. So in this case, I'm going to put sodium ions and nitrate ions, and we'll just fill it full of sodium and nitrate. Cool. Now I like to think of the salt bridge. That's, oh, by the way, we call this a salt bridge. It's a bridge between the 2 solutions full of salt. So it's called a salt bridge. And that salt bridge is essential. Without that salt bridge, you have a dead battery. Cool. And again, I like to think of this as actually, giving us a complete circuit, but you're never going to see it actually phrased that way, although it accomplishes that. So what you're actually going to see is that the salt bridge's job is to keep the solutions neutral. So sometimes they try to get all technical with the wording. They say it maintains electrical neutrality of the solutions. So, okay, great. Either way you recognize it. So, but that's what it does. So if you look here, so if we said we started this reaction off, there was already zinc 2 plus in there. We're making more in the reaction, but let's just say we already started off with zinc 2 plus in there. Well, to get zinc 2 plus in there, you'd have to add a zinc salt, like maybe something like zinc sulfate. And so initially for every zinc ion, there was a sulfate ion. It was a 1-to-1 ratio from zinc sulfate. So, but as we start producing more and more zinc ions, as this reaction goes, all of a sudden there's going to be an excess of zinc ions, an excess of cations. And so what you're going to find is that anions, the NO3 here, have to flow into the anode so that there's no excess cations. It keeps the solution neutral. As we start producing more and more cations, we have more and more flow of anions to keep the solution neutral. All right, so on the other side though, instead of producing cations, we're actually consuming all of our cations. The copper 2 plus ions are getting used up. And so same thing over on this side though. Initially, we probably put in some sort of copper salt like copper sulfate to get the copper ions in there. And the sulfate ions aren't participating here, just the copper. But as those copper ions get used up, all of a sudden these aren't going to be present in a 1-to-1 ratio anymore. There's going to be not enough cations and too many anions. And so in this case then, we'll have the sodium ions flow into the cathode compartment to add a bunch of positive ions to replace the ones we just lost, keeping the solution neutral. So ions flow through the salt bridge, and it's convenient which way they flow. Anions flow to the anode, cations flow to the cathode, kind of making it easy to remember. And so a big point here is that in the wire up top that connects the electrodes, electrons flow through there. But in the salt bridge, it's ions that flow through the salt bridge. Cations to cathode, anions to anode, and we expect to remember both of those things. So again, electrons are traveling from anode to cathode through the wire. So, but ions travel through the salt bridge, anions to anode, cations to cathode. All right, now we've got to talk about what are referred to as cell potentials. And a cell potential is nothing more than like the voltage or the EMF. You might call it that as well. So it's measured in volts typically. And your cell potentials are, we're going to talk about both standard cell potentials and the non-standard cell potentials. And standard cell potentials are just cell potentials under standard conditions. I'll remind you from the thermodynamics chapter, that means that everything is present that's aqueous at 1 molar concentrations, or if it's gaseous at 1 atmosphere partial pressures. That's what standard conditions mean. All right, so for these standard cell potentials, we typically give you something called a table of reduction potentials to help you calculate them and stuff like this. So because a cell potential, just like delta G, can tell us if a reaction is going to be spontaneous. Now, delta G can be used to tell if any reaction is spontaneous. So like this one up here, we use this in our galvanic cell, and I told you this was a spontaneous reaction. So then what would delta G be? So it's going to be negative. So we learned in the thermodynamics chapter that delta G is negative for spontaneous reactions. So well, these cell potentials, which are often given a squiggly E, epsilon E, if you will. So, and sometimes just capital E. So, and sometimes they'll be nice enough to put a little cell. So Ecell is often how we say them very loosely. And turns out these voltages, these EMFs, these cell potentials for a spontaneous reaction need to be positive. And you can only use these for redox reactions. So normal reactions that aren't redox, they don't have E cells. So, but it turns out these are often more convenient to use for redox reactions. And it's not that delta G can't tell us if a reaction is spontaneous. It can tell any reaction is spontaneous. But in this chapter, we're probably going to more commonly talk about E cells to figure out if a redox reaction is spontaneous. And keep in mind, it's not that both of these have to be true. You're not be like, well, I got this redox reaction, E cell is positive, but I don't know if delta G is negative. Well, it turns out these are actually mathematical functions of each other. If your E cell is positive, your delta G will be negative. It's always true. They're mathematically related to each other in such a way. So you only got to know if one of these is true to know if a reaction is spontaneous. And again, in the last chapter, we dealt with a lot of delta G, but in this chapter, it's going to be all about E cell. And when E cell is positive, we got a spontaneous reaction. All right. So how do we use a table of reduction potentials? So to figure out if a chemical reaction or a redox reaction typically is spontaneous. So if we take a look at the one we had here that we did with our galvanic cell, I told you it was spontaneous, and it's going to be spontaneous under standard conditions, and it's going to have a positive standard cell potential. And so if we break this up in our two half reactions here, we've got copper 2 plus going to copper. Just like down here, we have copper 2 plus going to copper. So, and there's a voltage of positive 0.34 volts associated with that. Okay. If we look up here, we've now got zinc going to zinc 2+. And if you notice, we've got in our table of reduction potentials, they only list them as reductions. They don't list oxidations, and that's an oxidation. Well, as a reduction, it's zinc 2+ to zinc, and it's negative 0.76 volts. But we're doing the exact reverse reaction. And if we do the reverse oxidation reaction, it's not negative 0.76 volts anymore. It's actually positive 0.76 volts. And so if we again take a look at this for copper, so again, copper 2+ to copper, written as a reduction, just like it shows up in the table, that's positive 0.34 volts. So, but for the zinc, again, we're going from zinc to zinc 2+, instead of negative 0.76 volts, it's going to here be positive 0.76 volts. And then we can just add these two numbers together, and we see that 0.76 plus 0.34 is going to get us an Ecell of positive 1.10 volts. Cool. And if you kind of take a look at breakdown what we just did, we said that Ecell, if I can write a good looking epsilon again, was equal to E reduction plus E oxidation. Cool. And our reduction half was that positive 0.34 volts. And the oxidation, after we had changed the sign, was positive 0.76 volts. Cool, and we just add them together and we get 1.10 volts. Now we have a problem though, is that this is often presented this way or one other way. Now I like this way. I think it's, nice that if a reaction's going forward, there's your potential. And if it goes backward, change the sign. Just like we would do with delta G, delta H, or delta S in thermodynamics. Change the sign for the reverse reaction. So that's why I in principle like this. So, but the early electrochemists, they didn't actually do this calculation this way. What they did was this. They said Ecell equals, I guess we'll go E cat minus E anode. So they said use cathode minus anode. If we got more specific with this though, we'd say E reduction at the cathode minus E reduction at the anode. And that's where things get a little bit crazy, because at the cathode reduction occurs, and that's good. But at the anode, that's where oxidation occurs. Why are we using a reduction potential at an anode? So, and that seems a little bit backwards. And they say, what they're essentially saying here though, is that never change the signs on these. We're going to change it for you by subtracting. Notice we added up here, but they're saying the subtraction will change the sign on the one that needs to be changed for you. And so the way they would perform this calculation is they'd take the positive 0.34 volts and they would subtract the value right off the table for zinc. They wouldn't change it to positive 0.76. They would leave it as negative 0.76 volts. And you're still going to come out with 1.10 volts either way, but this adds a whole layer of confusion to things. So the big mistake you can make is that you change the sign yourself and then you subtract it as well. So don't pull that off, because again, subtracting here changes the sign for you. So you got a choice now. You can change the sign like I did at first, and then you just add them together. Or you can not change any signs ever and make sure you do cathode minus anode, the values right in the table as they come. And the subtracting part of it changes the sign for you. So be careful. This is a point of contention here, and students mess this up. And again, I like this first one. I think this is really important, and it's useful in a couple other places down the road in this chapter. But again, it's very commonly taught this second way. So whichever way you do it, just make sure you're doing it right, and you got a method that's consistently reliable for you. All right. Now it turns out voltage here, so we've done one example. We'll do a few more here in a second, but we got to talk about the relativity of voltage. So it turns out voltage is a funny thing. We can measure voltage changes, but we can't say that something has so many volts. So it's always relative. It's just comparing two things, and so it's always relative. And so that's kind of a problem. So it turns out like we've got voltages explained, ascribed to each one of these reactions when it's all by itself, not being compared to anything. Well, it turns out every one of these values comes from a comparison to something. They took what's called the standard hydrogen electrode. So standard hydrogen electrode, which is this guy right here. And they just arbitrarily decided that's what we're going to call 0 on the voltage scale. Okay. So you're supposed to know this standard hydrogen electrode, so H plus going to H2, and it's 0 in both directions. And you're supposed to know that it's 0. Everything else, when you hook it up to this guy, that's when they give these values. So kind of a funny thing. So, but just keep in mind that voltages are all relative, and this is the one value we expect you to know. The standard hydroelectrode is 0. All the others you're going to be provided with, but not this guy. You're supposed to know he's 0 right from the get-go. Cool. Other than that, you're typically going to be given a table of reduction potentials. So if you're following along on my study guide, they're on the next page, by the way, the whole table of them. I only got a smattering of them here. There's a few more on the table that I provided for you. Cool. So I just want to take a second out to talk about the standard hydrogen electrode. I also want to point out one other thing. In the standard hydrogen electrode, if you notice, you've got H plus aqueous, and you've got H2 gas. But in this half reaction, there is no metal. So no solid metal at all, no metal at all. And so you couldn't use either hydrogen gas or H plus dissolved in water to make an electrode. And this would be a great example of a half reaction where you have an inert electrode. And in fact, platinum is the most common inert electrode we use for just such a half reaction. Just wanted to point out an example of where we might see that inert electrode. All right. So we've got a few questions now for calculating cell potentials. We want to calculate the cell potential for this reaction right here, this reaction right here, and then we'll have a little bit different of a question on the last one here. So in this case, I'm going to use the first method where if I see the oxidation and it's backwards, I'm going to change the sign myself and then just add them together at the end. All right, so first we've got zinc 2 plus going to zinc. And again, that's exactly how it shows up in my table. It's not backwards this time. So this is going to be negative 0.76 volts. And then we've got cobalt going to cobalt 2 plus, and this is the one that's backwards. We're actually doing this in reverse. And so instead of negative 0.28 volts, we'll do positive 0.28 volts. Cool. And again, because I changed the sign myself, we're just left just to add those together exactly as they are. And so in this case, negative 0.76, so, and positive 0.28 is going to get us, oh, not positive. How about 0.48 volts? Cool, and that would be our standard cell potential, the voltage associated with this reaction. So in this case, would this reaction be spontaneous under standard conditions? And hopefully you said no because it had a negative Ecell. So if I give you a balanced reaction, nothing says I have to give you a galvanic reaction. I could give you an electrolytic reaction. And so in this case, this is not spontaneous under standard conditions because it has a negative standard Ecell. All right, let's go to the next one here. So for the next one, we've got chromium 3 plus going to chromium. And for chromium 3 plus going to chromium, negative 0.74. It's in the direction where, it's in our reactions in the direction it's written, and so we'll put negative 0.74 volts. So, and one thing to note, you might be like, hey, Chad, it's doubled. And you're right, it is doubled. And if we were dealing with delta G, delta H, or delta S, I'd tell you to double the delta G, delta H, or delta S that you might, be accompanied with this. But not for voltages. It turns out, it doesn't matter if you're doubling this reaction or tripling it, that doesn't change a thing. So it turns out a volt is a joule per coulomb. And if you double this half reaction, you double the joules, the delta G, turns out. But it turns out you also double the coulombs, and coulombs is a measure of charge in physics. So if I double this half reaction, it would now become 6 electrons, which would be twice as much charge. And so you're doubling the joules, and you're doubling the coulombs. And so the ratio of joules to coulombs, i.e. volts, would be exactly the same. So just key note when we're doing standard cell potentials, if you've got coefficients, don't factor them in like you would. Again, if you were calculating delta G, delta H, or delta S, you'd totally factor them in, not for voltage. All right, so then we've got copper going to copper 2 plus. And again, with copper to copper 2 plus, this is the one that's going backwards now in this example. And so instead of positive 0.34 volts, we'll have negative 0.34 volts. And then again, because I took, the effort to change the sign myself, we'll just add these together and we're going to get negative 1.08 volts. And once again, my question for you is, would this reaction be spontaneous under standard conditions? And hopefully, yet again, you said no with this negative Ecell. All right. Finally, last question here we're going to deal with is a little bit different fundamentally. And on the handout here, it says, what is the balanced reaction for the galvanic cell? It's part of the question here, so write that down. So galvanic cell, really important, composed of MnMn2 plus and Fe2 plus. So this is a little different question. I didn't give you a balanced reaction, first of all, but I did tell you it's a galvanic cell. And if I told you it's a galvanic cell, you know that the E cell has to come out positive. Notice on these ones up here, I just gave you the balanced reaction. Nothing, I never said galvanic cell, I just said get me a cell potential. Nothing told you it had to come out positive or negative, you just go whatever it came out as. And these just both happen to come out negative. But on this one, I didn't give you a balanced reaction like I did here, but I told you whichever way you work this, you better come out with a positive E cell. And so if we look at the two half reactions we have in this one now, so we're dealing with Fe to Fe2 plus and Mn2 plus, which I didn't put on there. Let's write that in real quick. And like I said, if you're following along on the study guide, it is on the very next page. And it would be way at the top here. So we'll squeeze it in. Mn2 plus 2 electrons going to Mn, negative 1.18 volts. Double check that. Yeah. All right, so these are our two half reactions we're now dealing with. And again, we're making an oxidation-reduction reaction. So they're both written as reductions. One of them is going to have to go backwards and be an oxidation. So somebody needs to gain electrons, but somebody needs to lose electrons as well. In this case, though, I've got to be careful which one I do. I have to be specific about which one I do, because if I do the wrong one, it won't be spontaneous. It's only going to be spontaneous in one direction. And so if you look at these two values here, whichever one I have go reverse, it's going to change the sign. Now, let's say I choose iron to be that just randomly here, 50-50 guess, right? If I change the sign and make that positive, 0.44 volts, then when I finally add that to negative 1.18 volts, it's not going to come out positive. That would have been wrong. And so I figured out that the one that's less positive or more negative is the one I actually have to make the oxidation, the anode, and go in reverse. That's the only way I'm going to come out with an overall positive E cell. So this is the one we're doing backwards. And so I'm going to write a balanced chemical equation out of this, and then we'll calculate the E cell to go with it as well. And so in this case, we're going to start with Mn as a reactant, in the one that's going backwards, and then Fe2 plus the reactant in the one that's going forward. And that's going to form some Fe and some Mn2 plus. And they're both two electron processes, so it's balanced. And in this case, again, our Fe to Fe2 plus is exactly what we see on the table, and so it's negative 0.44 volts. But the Mn to Mn2 plus, we designed it to be exactly backwards of what's on the table. And if what's on the table is negative 1.8 volts, then this is going to be positive 1.18 volts. And again, if I took the time to change the sign myself, then I can just add these, not subtract. Cool. If we look here, 9.8 plus another 24 is 0.74 volts. I think I did that right. For our E cell here. And again, we designed it to come out positive. It had to come out positive because we were told it was a galvanic cell. Notice if we'd done the exact reverse reaction instead, which would have had the iron reaction going backwards, it would have come out to negative 0.74 volts. But because we were told it's a galvanic cell, we had to make sure it came out positive. So now we've calculated standard cell potential, so cell potentials under standard conditions when all aqueous species are 1 molar and all gases are 1 atmosphere. What if we don't have those standard conditions? What if we have non-standard conditions? And we have an equation for that. I just want to remind you that we had an equation for that for delta G as well. And to calculate delta G under some non-standard set of conditions, you start with the standard value and add in this fudge factor. And that fudge factor takes into account with the reaction quotient any concentrations that are not 1 molar. Now, it turns out we have a very similar one for the E cell. So here we've got, if you want to calculate your your cell potential under non-standard conditions, you start with the standard value and then add in this fudge factor yet again. Okay, So it involves Q, but it involves a couple extra things here as well. So we've got F, and F is called Faraday's constant. So in Faraday's constant, it's 96,500-ish, or 485. Some people say so 96,485. But we're going to round it to 96,500. And what it really is that the amount of charge in coulombs on 1 mole of electrons. So there's 96,500 coulombs of charge on 1 mole of electrons. That's where that number really comes from. It's a constant, and most of you probably won't have to memorize it, but if your professor is really keen on you memorizing everything, well, then you might be stuck on that one. But most of you probably won't. Probably given to you. So this is called the Nernst equation. So, and if you look, you got this RT over NF. Now, N is the number of moles of electrons being transferred either in your half reaction or your whole reaction. So we'll figure that out pretty quickly. So, but R, T, and F. So F is Faraday's constant, 96,500. R is the universal gas constant. In this context, we'd use 8.314 joules per mole Kelvin. So, and then T is just your temperature in Kelvin. Now, it turns out this equation is often just simplified for a lot of Gen Chem students, and we just say, you know what? As long as we're just talking about only 25 degrees Celsius, only 298 Kelvin, then this would really just be a constant times the 298 Kelvin divided by a constant and then N. And we could combine those other three constants, again, assuming we only ever talk about 298 Kelvin, into a new constant. And it could become 0.0257. Still keep the N, because that can be different still, depending on what half reaction or whole reaction you're talking about. And it turns into this equation as well. So students are often given this equation as well. And because natural logs kind of suck when you don't have a calculator, and 100 years ago they didn't have calculators when they pioneered this math here. So in this case, sometimes you'll see this equation expressed with a log base 10 as well. And it turns out that 2.303 is the factor that makes log base 10 and natural log equal. And so if you take and multiply this by another factor of 2.303, you get a slightly different constant, and now we can use the log base 10. So in all likelihood, you're given one of these three equations. Maybe you're even given all three. So any one of them leads you to the same place. So I'm probably going to use this middle one when I do my calculation here. So it's pretty standard to be given this middle one now. So, but 10 years ago, it was still pretty common to be given this one, even though calculators have been around for a long time. So, but c'est la vie. All right, so non-standard cell potentials. The hallmark of a non-standard cell potential is that you don't have 1 molar concentrations of everything. And so the next question on your study guide there says, calculate the cell potential for the cobalt zinc cell we dealt with in the previous problem. So I left that up there. So, but with a concentration of zinc ions of 0.001 molar and a concentration of cobalt ions of 0.1 molar. So these are not 1 molar. And so we figured out earlier that the standard cell potential was negative 0.48 volts. But we're not under standard conditions, so it's not going to be equal to negative 0.48 volts. And we're going to use that Nernst equation to figure out what it actually is. So in this case, again, we'll say E equals E standard minus 0.0257 over N log of Q. And Q in this case is products over reactants. And keep in mind that the zinc and cobalt here are solids, and they're not going to show up in Q, but cobalt 2 plus and zinc 2 plus as ions are going to be aqueous, and they're going to show up in Q. And so our Q here technically is going to be the cobalt 2 plus over the zinc 2 plus concentration. And keep in mind, if we had coefficients, we might have to square or cube something or something like that. But in this case, they're both coefficients of 1. All right, and from here we'll plug in chug. What's convenient is we already figured out the standard cell potential that we need to plug in right there. Had we not already previously done this problem, that would be step 1, is figure out that standard cell potential from a table of reduction potentials. But we've already completed that. And so in this case, we're just going to have E equals negative 0.48 volts minus 0.0257 all over N. Now, N here is the number of moles of electrons transferred. So, and if we look at this reaction here, whether I'm going from cobalt to cobalt 2 plus and losing 2 electrons, or whether we're going from zinc 2 plus to zinc and gaining 2 electrons, this thing has been balanced to a transfer of 2 electrons. And that's what goes right here. Now, it turns out you can do an equation like this, the Nernst equation, for either a complete balanced reaction or for any half reaction. And when it's the half reaction, you just plug in the number right out of the half reaction for the number of moles of electrons. That's easy. So, but for a perfectly balanced reaction, the electrons don't show up in there, and you kind of have to, work out the process like we just did to figure it out. Now, one thing to note, here it was 2 either way, so it's easier to figure out it was 2. But if you recall, when we balanced reactions at the beginning of this section, the one involving permanganate and I- and stuff like that, we had 2 electrons in one half reaction and 5 electrons in the other, and we ended up balancing the whole reaction to 10 electrons. That's what N would be for that particular reaction. It's whatever you've balanced the whole reaction to. So, and Cool, just wanted to give you an example of that because that gets a little bit tricky for some of those more complex redox reactions. All right, so let's keep figuring this out. And oh, I jacked this. That's not supposed to be log base 10. That's supposed to still be natural log. My apologies, guys. So natural log. So if you've been screaming at your screen for the last 5 minutes, my apologies. Cool, it is natural log. And in this case, we'd have natural log and cobalt concentration again is 0.1 molar over the zinc concentration of 0.001 molar. And from here, it's going to be plug and chug. And if you work this out, so cool. If you want to take the time to work this on your calculator, I'm just going to give you the answer here, so you might pause it for a second, but I get negative 0.54 volts. Cool, so this thing's even less spontaneous than it is under standard conditions with this set of conditions. And we might have been able to predict that. So let's talk about this for a second, a little more here. So let's say under standard conditions, Ecell for this is negative 0.48 volts. My question for you is, what would the cell potential be, not the standard, but what would the cell potential be for this reaction when it reaches equilibrium? And before I ask that, I might ask you, what's delta G when the reaction reaches equilibrium? And hopefully remember that delta G is 0 for reactions that reach equilibrium. Well, the same thing's true here. It's not the standard value, but the non-standard value for the cell potential also approaches 0 as a reaction proceeds towards equilibrium. And when it finally reaches equilibrium, it's equal to 0. So let's say we let this reaction reach equilibrium. Well, at that point, E cell is going to be 0. Okay. And then let's do some things with Le Chatelier's principle. Let's say I dump a bunch of zinc ions into the solution. Well, if dump a bunch of zinc ions into the solution, it's no longer at equilibrium. And we'd say that the reaction needs to shift to the right. Well, shifting to the right is the same thing as saying that now the forward reaction is spontaneous. And if the forward reaction is spontaneous, we just ended up with a positive E cell. Also a negative delta G, but a positive E cell. And so what we just kind of demonstrated, though, is that if you get a shift to the right, according to Le Chatelier's principle, that always causes E cell to get higher and delta G to get lower. So E cell to get more positive, delta G to get more negative, if you will. Cool. On the other hand, let's say, again, this reaction reaches equilibrium so that E cell is 0 again. But instead of dumping a bunch of zinc ions, I dump a bunch of cobalt ions in instead. So in dumping a bunch of cobalt ions in, all of a sudden now we're not at equilibrium anymore, which means E cell no longer equals 0. And by dumping a bunch of cobalt 2+ ions in there, it's going to shift the equilibrium back to the left. And in shifting the equilibrium back to the left, that means the reverse reaction is spontaneous. And if the reverse reaction is spontaneous, it means the forward reaction is not spontaneous. And so the forward reaction, as it's written, being non-spontaneous, means that E cell is now negative and delta G is now positive. And so anything that causes the equilibrium to shift to the left causes E cell to go down, get more negative, and causes delta G to go up, get more positive. Cool. So we can do calculations with the Nernst equation, and you're probably on the hook for that. But you should also just kind of realize some qualitative understanding there of what a shift to the left or right causes in terms of both E cell as well as delta G from last chapter. All right, now that we've learned non-standard cell potentials and the use of the Nernst equation, I just want to take a quick shout out about a special type of galvanic cell called a concentration cell. And what's unique about a concentration cell is that your anode and your cathode are made of the same stuff. So in this case, I'm going to make my anode out of copper metal and the cathode electrodes made out of copper metal. And in the solutions on both sides is also going to be copper ions. So we're going to connect those solutions, and I guess I should draw in those solutions here. We'll still connect those solutions with a salt bridge. That's still required. But I'm not going to focus on it in this point. There's salt in there. Great. Life's good. But we got the same stuff on both sides, and this is kind of a weird thing. And so if you look at what's going on at the anode, well, oxidation occurs here. So copper is the reactant, copper 2+ is the product. But at the cathode, that's where reduction takes place. So copper 2+ is the reactant, and copper is the product. And so you have the same stuff, and you actually even have the same reaction going on in both sides, but in opposite directions. One's oxidation, one's reduction. And so this is kind of a funny thing. So it turns out if we look at the standard cell potential here, well, again, for my reduction here, we get it right off the table, written as it is, and it's positive 0.34 volts. Cool. But the oxidation is exactly backwards, and again, I like changing the sign, so this would be negative 0.34 volts. And so your standards, when you add them together, and so your standard cell potential has to be 0. And that's true for any concentration cell. Because you have the same exact stuff on both sides, but in opposite directions, your standard cell potential has to be 0 in a concentration cell. And so if this scene's going to actually act as a battery, well, it can't be under standard conditions because that's not going to be spontaneous at all. That's at equilibrium. And so we don't ever operate a concentration cell under standard conditions, so we do it a little bit different. And so what we do is shift the equilibrium to the right a little bit, if you will. And so if I look over here, if I want to shift this equilibrium to the right, well, then I want to have a low concentration of copper 2+. So I'm going to write that over here. We'll put low concentration over here in the anode. And if I want to shift this half reaction to the right, then I want to have a very high concentration of copper 2+. Cool. And both of those are going to cause this. Now, I say low and high, and really it's just lower and higher. They can't be equal. If the two concentrations are equal, then you've got, at that point, a dead battery. Ecell is 0. All right, so if we kind of take a look at what's going on here, on the side where the concentration is low, you're producing more copper 2+. And so even though it starts off low, that concentration is going to be going up over time. And on the side where the concentration of copper 2+ is high in the half reaction, so on this side you're actually using up your copper 2+. And so even though it starts off high, over time it will be going down. So, and as those two concentrations over time start approaching each other, when they finally reach each other, that's when Ecell gets to 0. And so this battery is just continually running down until the Ecell gets closer and closer to 0 and finally reaches 0 when they're equal and at equilibrium. And so in a sense, you can kind of think like diffusion, in a sense, is kind of powering this thing. It's one way to look at it. So, but as a result, then, if we're never running these under standard conditions, then you always have to use the Nernst equation. So to calculate the cell potential in a concentration cell. So once again, I'll use the middle version here of our Nernst equation. Cool. Big things here is that E standard for any concentration cell is always 0, and students usually get a little confused by that. They kind of a little unfamiliar with concentration cells. So in our case, this would be E equals 0 minus 0.0257, and we can see that it's 2 electron process. 2 electrons either, oh, look at this, I jacked it, no, I did this. Cool, 2 electrons lost, 2 electrons gained, it's balanced with 2 electrons. And then ln of Q here, and Q is where students get confused. So which concentration do I put on top, which do I put on the bottom? So, and there's a couple of different ways to look at it. Well, one, if you do it backwards, you'll end up with a negative E, and that's wrong. So if you do it right, you'll get a positive E. So if you do this wrong and get the negative value, just change the sign. Some people say that. So, but if you look at what's really going on here, in terms of copper 2+, in the anode side, copper 2+ is a product, so that goes on top. And so here we'd have copper 2+ from the anode on top. So, but on the cathode, copper 2+ is the reactants, and so on the bottom we'd put the copper 2+ concentration from the cathode. And some people will look at it that way, and some people say, well, you know, I mean, it has to be lower in the anode and higher in the cathode. And so instead of saying anode over cathode, some people will say do this low concentration over high concentration. And only if you do it low over high will you come out with a positive Ecell. Had you done it high over low, or cathode over anode in this case, then you would have come out with a negative Ecell. Cool. So whether you remember how to do this exactly, or whether you remember that it has to come out positive, so if it doesn't come out positive, just change your sign after your calculation, great. So, but I just wanted to work it out so you knew in principle why one goes on top and one goes on bottom and which is which. Cool. Those are concentration cells. All right, before we move on, I wanted to interject one little thing here. So we're talking about non-standard cell potentials and stuff. Sometimes we ask these questions, and instead of giving you a balanced reaction, stuff like this, sometimes we use a special cell notation instead. And the way this cell notation works is we'll put the anode on the left, just like we did when drawing the diagrams, if you will. We'll put the cathode on the right. So, and the way this works is your anode reaction here, so is cobalt going to cobalt 2+ for that last one we did. And so we'd put those over here with the anode, and you'd put the reactant first, typically is the way they should draw it. So cobalt, and then you'd put cobalt 2+. So, and for aqueous things, then you'd also include in parentheses their concentration. So here I'd put 0.1 molar. Cool. And when two half cells are physically separated, you put a double slash. So you put a single slash here. If your two reactants, if the two species, reactant product, in your anode are of different phases, and here one's solid, one's aqueous, so they get a slash between. And then for separate half reactions, you put the double slash because they're in separate half cells. So, and then on the other side, we've got zinc 2 plus as the reactant, zinc as the product. So we got zinc 2 plus slash zinc, and again a slash between them because they're in different phases. One's aqueous, one's solid. And for zinc 2 plus, we also want to put his concentration in parentheses. Cool. So instead of giving you a balanced reaction and giving you the concentrations, I could have just simply spelled this out right here and said, hey, what's the cell potential? What's the voltage of this battery? And a lot of students have never seen this kind of notation. They're like, what's going on? But again, the key is anode on the left, cathode on the right, and they give you all the concentrations. So when you see concentrations that are not 1 molar, you should be like, oh, that's non-standard conditions. I need to use the Nernst equation. Cool. So I just want to make sure you've seen that cell notation at least somewhere once before you take an exam on this stuff. All right, I want to get an expanded table of reduction potentials to match the one that's on your study guide. Let's follow it along, and we're going to use this quite a few times throughout the rest of this lecture, so put it all up on the board. We'll keep it there so I can refer to it. And when you've got a table of reduction potentials, there's a slew of questions you can now answer. And so often on an exam on electrochemistry, they'll give you a table like this, either in the question or like on the front page of data and stuff like that. So if we look, so some questions we can answer by being given a table of reduction potentials is which of the following is the strongest oxidizing agent, which of the following is the strongest reducing agent, or which of these pairs react together spontaneously. And so we'll pick these apart as we go here. So in this case, if I want the strongest oxidizing agent, well, you have to remember that the strongest oxidizing agent gets reduced, or that any oxidizing agent gets reduced. So first of all, you have to realize, and if you recall, we also said that oxidizing agents and reducing agents are always reactants in a reaction. So keep that in mind. So if oxidizing agents get reduced and they have to be reactants, well, then when I look at a table like this, these are written as reductions. First off, check, halfway there. And these are the reactants. And so my correct answer here has to be one of these on the left. So the right answer could be Al3+, it could not be Al, not as an oxidizing agent. Oxidizing agents get reduced, and they're the reactants in a reduction. So, but in this case, if I want the strongest oxidizing agent, then I want the most spontaneous reduction, which means the most positive Ecell. And in this case, that ain't aluminum 3+, that actually would be true for Br2 on our list. Now, just because it's the biggest one, most positive one on our list, amongst 5 answer choices, they don't actually have to give you this one. They just say which of the following is the strongest oxidizing agent. But if we were going off this complete list, then yeah, our answer to this question would be Br2. Notice it would not be Br-, it would be Br2 as the correct answer. Now, the trickier question is, instead of asking you about the strongest oxidizing agent, is if I ask you for the strongest reducing agent. And this is tricky because reducing agents don't get reduced. Reducing agents get oxidized. And so if we look there, these are all written as reductions. I don't need those. I need to look at all the reactions exactly backwards as oxidations. And so in this case, the reactants in all the reverse reactions are aluminum, manganese, zinc, not Al3+, Mn2+, zinc 2+. And so for the reducing agents, I now need to pick one of these. These are the reactants in the oxidations going the other way. But also, if I'm looking at all the reactions going backwards, that changes all the signs on everything we see. And so this gets tricky. And so if I want the strongest reducing agent, I want the species that is most spontaneously oxidized. And realizing that, again, it has to be one of these over here that, again, are reactants in the reverse reactions, because those are what are getting oxidized. And to be the most spontaneously oxidized means I want it to be the most positive after we've changed the signs. And on our list, that would be plain old aluminum here. Now, this is tricky, and a lot of students will tell me, Chad, I was told that if I wanted the strongest oxidizing agent, I look for the most positive value. And if I want the strongest reducing agent, I look for the most negative value. Well, sorta. So if you want the strongest oxidizing agent, you do look for the most positive value on a table of reduction potential. That's true. But then you got to make sure you pick the correct side when you're looking for the oxidizing agent, the guy who gets reduced. So if you're looking for the strongest reducing agent, again, they told me, well, my teacher told me to look for the most negative value. Well, that's true. The most negative value before you change the sign. And again, you have to know which side is actually the proper reducing agent as well. And it's what's written as the product in the forward reaction, but it's the reactant of the reverse reaction. And so plain old aluminum, not aluminum 3+, and after you switch it, it would have the most positive value. So be careful. If you make these generalities, it's the most negative value. Well, it's the most negative value before you change the sign because you're looking at the reverse reaction. So hopefully I've made myself clear on how you distinguish that, but that second one is definitely the trickier of the two, so be careful. All right, last but not least, we're talking about which pairs react spontaneously, and they're going to give you a bunch of pairs, and it has to be stuff that you've got a table of data for. Now, you have to realize, first off, that they're talking about, when they say react spontaneously, an oxidation-reduction reaction. So being an oxidation-reduction reaction, you have to have somebody that can get oxidized, that can lose electrons, mixed with somebody that can get reduced, that can gain electrons. So again, these are all the guys getting reduced as reactants in these reduction half reactions. But you need to mix one of these over here with one of these over here that can get oxidized in the reverse reaction. So if you just mix two of these on the left, they're like, I can get reduced and I can get reduced. And there's no such thing as a reduction-reduction reaction. So, and that's why this first example, we can just cross it out. Don't have to evaluate it at all. I see Cr3 plus CO2 plus, Cr3 plus CO2 plus, they both can get reduced according to the data I have. There's no such thing as reduction-reduction. So there's also no such thing as oxidation-oxidation, which is why we'll cross off this example, just plain old chromium and cobalt. Now, chromium as a reactant is a reactant in the reverse oxidation half reaction, and cobalt as a reactant would be a reactant in the reverse oxidation half reaction. And so according to the data we have, we only have evidence of chromium and cobalt ever getting oxidized, never reduced. And so there's no such thing as an oxidation-oxidation reaction, so it's just impossible. I don't have to look at numbers, nothing. We're done. It's not possible. Not going to react spontaneously. It's just two metals. All right. So, but now if I do give you one from each side, you do then have to go through and figure out, is it spontaneous? Will it have a positive Ecell, so to speak? So Cr3 plus and CO. And so in this case, I'm giving you Cr3 plus right here and CO right here. And so I am giving you a species that can gain electrons and get reduced, and I am giving you a species that can lose electrons and get oxidized in the reverse reaction. But now I just have to figure out if it's spontaneous. And for Cr3 plus getting reduced, it's negative 0.74 volts. But for CO getting oxidized, if I change the sign myself, it would be positive 0.28 volts. But negative 0.74 and positive 0.28 is not going to come out to a positive value. And so because it has a negative Ecell, it's not spontaneous. So then finally, if I give you chromium and cobalt 2 plus, so now chromium over here, cobalt 2 plus over here. And so now I'm giving you cobalt 2 plus who can get reduced, and I'm giving you chromium who can get oxidized in the reverse reaction. And so cobalt 2 plus getting reduced is negative 0.28 volts, but chromium getting oxidized in the reverse reaction would be positive 0.74 volts, and negative 0.28, positive 0.74, we now are going to have a positive Ecell. We did get a species, one that could get oxidized, one that could get reduced, and it led us to a positive Ecell, and these two would react together spontaneously in a redox reaction. All right, we've got a little math deal within this chapter. We're going to relate it back to the thermodynamics of the last chapter. So, and it turns out we've dealt a lot with Ecell, and we've learned that it can tell us if a reaction is spontaneous, but in the last chapter we learned that delta G could tell us if a reaction was spontaneous, and it turns out they're related through this lovely relation right here, and you might have to do some basic plugging and chugging here. And so delta G equals negative NFE, and N is still the number of moles of electrons transferred in our reaction or half reaction. F is still Faraday's constant, 96,500 joules per coulomb. So, and then E is your standard Ecell. And you can use this relationship both under standard conditions, but also under non-standard conditions, it works as well. Cool. In fact, if you take one of our thermodynamics equations that relates delta G to delta G standard and substitute these both in for delta G and delta G standard, that's actually where the Nernst equation comes from. All right, we also learned that there's a relationship between delta G standard and the equilibrium constant, and similarly, there's also a relationship between Ecell standard and your equilibrium constant as well. And so the big point of this here is we've got a bunch of equations that relate these things, but delta G standard, E standard, and the equilibrium constant, they are all mathematically interdependent upon each other. So if you've got a delta G standard that is negative, well, that's a spontaneous reaction under standard conditions. So, and if it's negative, then Ecell standard should be positive. It's a spontaneous reaction under standard conditions. And again, if your delta G standard is negative and your standard Ecell is positive, if it's spontaneous under standard conditions, then you're going to start turning reactants into products from those standard conditions and end up with more products than reactants, and your K is going to be bigger than 1 as well. So you should know those relations, but also you're going to might have to do some simple plugging and chugging here. So the galvanic cell we dealt with earlier was this guy right here. We already calculated out that the standard Ecell was 1.10 volts there. And so we're going to start with that Ecell, and we're going to get both delta G standard and KEQ. Again, if you know any one of these three, these equations allow you to calculate the other two. So I'm going to start with Ecell and get the other two. And so the first calculation we'll do here is delta G standard equals negative NF E standard. And in this case, we'll get negative 2 for the number of moles of electrons transferred. Either copper 2 plus to copper is 2 electrons gained, or zinc to zinc 2 plus is 2 electrons lost. So it's 2 electrons transferred. So, and then we've got, in fact, you know what, let's do units here. Units are important here. So 2 moles of electrons. Faraday's constant is 96,500 joules per, actually, let's get that right, coulombs per mole of electrons. And so here the moles of electrons part is going to cancel. And then finally, we've got the 1.10 volts for the E standard. So, and we'll put that in there, but you should know that a volt is a joule per coulomb. So if we go substitute that back out, instead of volts, we put in joule per coulomb, then we'll see the coulombs part here is also going to cancel out, and we'll get an answer in joules. And I did this just a minute ago, and so I'm just going to give you the answer. So if you're still working this out, you might pause the video. So, and I got negative 2,12300 joules, which is probably going to be written more properly in kilojoules, but depending on you know, who wrote your test and stuff, it could be either way, but I'd probably give this to my students as negative 212.3 kilojoules. But take your pick. We just calculated delta G standard, and again, we had a big fat positive E cell standard, so it told me it's spontaneous under standard conditions, and yeah, that should have given us a negative delta G standard, again, spontaneous under standard conditions. And finally, we'll calculate the equilibrium constant. Now, in this case, we could use this relationship here from the thermodynamics chapter. Now that we know delta G standard, we could calculate KEQ. But we could also have done it just separately from this chapter, because we already had E standard, and we could get KEQ as well. So if you already had E standard, you could take the long way around and use E standard to get delta G standard, and then delta G standard to get K, or you could just go there directly here, and that's what I'm going to do. And so in this case, we've got 1.10 volts equals 0.0257 over 2 moles of electrons times the natural log of KEQ. And if we rearrange this and solve for that KEQ, it's going to be e to the power of 1.1, my dyslexia creeping up. So 1.10 volts times 2 moles of electrons all over 0.0257. By the way, it's implied that this is all being done at 298 Kelvin. Otherwise, these constants don't apply. So they'd have to give you that in the problem as well. All right, and if we work this out, and like I said, I'm just going to give you the answer because I worked this out already. We get 1.5 times 10 to the 37th. Cool, that is a huge equilibrium constant. It heavily, heavily, heavily favors the products as compared to the reactants at equilibrium. Cool. And again, we should expect that, and you may not expect the number-wise, but at least you should have known this should have been quite a bit bigger than 1, because we had both a positive E cell standard, a negative delta G standard, which definitely means that the product should be favored, so we should get a K that is bigger than 1. All right, now that we've learned some new stuff this chapter, I just want to do a quick review of all the different ways we've learned to figure out if a reaction is spontaneous. And when people talk about having a spontaneous reaction, they're usually 9 times out of 10 probably talking about delta G. And when delta G is negative, i.e. less than 0, a reaction is spontaneous. But we learned in this chapter for redox reactions, we might also look at the E cell instead. And when your E cell is positive, greater than 0, a reaction is spontaneous. Now, a couple other ways we could look at this as well. So technically, we learned that when Q is less than K, that the reaction needed to proceed to the right, like a Le Chatelier's principle type thing. Well, a reaction proceeding to the right means the same thing as just saying it's spontaneous in the forward direction. And so Q being less than K, or K being greater than Q, however you want to say it, also actually means a reaction is spontaneous. Now, we didn't use that word back in the equilibrium chapter, but we're using it now. Another way to figure out if your reaction is spontaneous. And finally, they could play with you a little bit. They could say delta H minus T delta S is negative. Well, because delta G equals delta H minus T delta S, this is really just the same thing as saying that delta G is negative. So they could, play with some of the other relationships, but in principle, we have three main ways to figure out if a reaction is spontaneous, and then some variance based on equations we know, and then ultimately we have the second law of thermodynamics. And the second law of thermodynamics just said that for a spontaneous process, delta S of the universe is positive, and that definitely tells you that a reaction is spontaneous as well. One of the laws of thermodynamics that tells us that. Cool. These are pretty much the ways, and like I said, they could take some of the equations that these are related to and kind of relate them, but most of the time it's going to come down to one of these. All right, so now we've got to have a discussion about electrolytic cells instead. We'll talk about them proper, and then we'll also talk about some crazy electrolysis calculations you might do for like electroplating and things of this sort. So but we'll start with electrolysis in principle. So the two types of major electrolysis we do, and again, we're going to ignore recharging batteries and counting that for a second. So, but typically we do electrolysis, and for it to be possible, you have to have mobile ions that can move around. And that's going to happen in one of two cases, either because you have a liquid salt. So, and salts have super high melting points. So when we have a liquid salt, we generally call it a molten salt, like molten lava. So it's super high melted salt. So super high temperature. Or if a salt dissolves in water, then you could have an aqueous electrolysis reaction going on as well. So we have molten electrolysis and aqueous electrolysis. And if you're doing them in principle, aqueous electrolysis, so you can often do it at room temperature and it seems easier, but you don't always get the products you want to get and stuff like that. Whereas molten electrolysis takes crazy temperatures, huge amounts of heat, lots of energy, and so in practice might be more difficult. So however, theoretically, we're going to see that on theory, on paper, molten electrolysis is much easier to deal with. Aqueous electrolysis is a little bit of a pain in the butt. So, but again, in both cases, you'd have mobile ions. So we'll compare our electrolytic cell to our galvanic cell. And one big difference you'll see is that instead of having two separate half cells, we're going to do this all in one compartment. And this kills the need for any sort of salt bridge or anything like that. We'll still put the anode on the left. We'll still put the cathode on the right. So, and in this case, I'm going to look at doing electrolysis with liquid sodium bromide. That's molten sodium bromide. And what we'll find out here is that we're going to have sodium ions. Let's put these in a couple of different colors here. We're going to have sodium ions, and we're going to have bromide ions just floating around in there. And this isn't water. This is just a melted salt. And melted salts have mobile ions floating around each other and stuff. What we'll find out here is that anions are going to go to the anode and cations are going to go to the cathode. It makes it easy to know here. So, and when the anions go to the anode, they turn into their elemental form. And so in this case, that's going to turn our bromide ions into elemental bromine, which is Br2. So, and because it started with the anion, it's easy for me to remember that that's going to happen at the anode. Now the cations, in this case, sodium starts off in sodium bromide in the +1 oxidation state, so it's our sodium ions. They're going to go to the cathode instead. And so our bromide ions went to the anode, and when they went to the anode, they got oxidized and lost electrons. Those electrons flow through the wire, and they don't want to flow that direction, but we have a power source hooked up that's forcing them to flow that direction. And then they sit on the surface of this electrode on the right here, and that's when the sodium ions bump into it. They gain those electrons, and your sodium ions turn into sodium metal. And again, that happens at the cathode. So what's nice in molten electrolysis is you can just say, well, the cation gets reduced at the cathode, the anion gets oxidized at the anode. Cation at cathode, anion at anode, and both turn into an element. And so as long as we're just talking about an ionic binary salt, a salt made of only two elements, no polyatomic ions, that's exactly how it works. I mean, it makes predicting the products really easy. Just both elemental forms. Instead of Na+1, it's Na in the 0 state. Instead of Br in the -1 state, it's Br in the 0 state. And you had to remember he was diatomic. So, and then you can figure out which one was cathode and anode. Well, in this case, if I'm going from +1 to 0, that's reduction. It happens at the cathode. And if I'm going from -1 to 0, that's oxidation. And that happens at the anode. Cool. So no need for a salt bridge in this case, but also note that this is also the direction that the electrons did not want to go. So it turns out now your anode, we pointed this out earlier, is now positive, whereas it's negative in a galvanic cell. So, and your cathode is now negative, it's positive in a galvanic cell. And so the electrons actually want to flow the other way, but the power source here is causing them to flow uphill energetically, if you will, opposite of the spontaneous direction. So we're forcing a non-spontaneous reaction to happen with the input of a power source, the input of electricity here. All right, so that's aqueous electrolysis. If I give you any binary salt, predicting the products is really, really straightforward. Cation to its elemental form at the cathode, anion to its elemental form at the anode, done. Now, if we do aqueous electrolysis, we have a problem. So, and the problem here, so with aqueous electrolysis, is we have more than just sodium ions and bromide ions to start with. Aqueous implies that there's also a bunch of water. And so now instead of just having a molten salt, this would mean there's a ton of water in here. And so it turns out water can get both oxidized and reduced, and that's a problem. So with water being possible to get both oxidized and reduced, it turns out when water gets reduced, so we'll go over here, when water gets reduced, it turns out we form hydrogen gas. And when water gets oxidized, it turns out we form oxygen gas. So, but because both of those are possibilities, it puts a wrinkle into figuring out who gets oxidized and who gets reduced and who's our products. Because now all of a sudden, water can get oxidized at the anode or bromide can get oxidized at the anode. And only one of the two is going to happen. And it turns out whichever one is what I'll call easier. And same thing over here at the cathode, either your cation can get reduced at the cathode or now water can get reduced at the cathode. And only one of the two is going to happen, whichever one is easier. So given you some data here so we can figure out which one actually is easier. So to figure out which one is easier, you'd need data just like this. So in this case, we've got, right off the bat, we've got the reaction for sodium ions getting reduced, and I compare it directly to the reaction of water getting reduced. And we said when water gets reduced, it forms H2 gas. It also forms hydroxide. And both of them have big, fat, negative reduction potentials. And so when I say, you know, the only one that's going to happen is the one that's easier, so, well, more positive means more spontaneous, and so easier in this case means either more positive or less negative. And so comparing these two, it means less negative. And so I see over here that it's actually the water in aqueous electrolysis that would actually be getting produced. And so in this case, we won't produce any sodium whatsoever. When the water gets reduced, we're going to produce some H2 and some OH minus instead. No sodium metal getting produced in aqueous electrolysis whatsoever. Cool, and we can see that that was negative 0.83 volts. All right, when we deal with the anode now, it's going to be a little more problematic. So, and it's more problematic because oxidation happens at the anode. And here I've given you two relevant reduction reactions with reduction potentials. So we're not going to look at these in the forward direction. We have to look at these in the, ooh, and I've got this backwards, don't I? Oh, no, I was nice. Oh, wow, look at this. I didn't write them as reduction potentials. I wrote them as oxidation potentials. I already flipped them around for you. So notice when electrons are on the reactant side, they're reductions. When they're on the product side, they're already oxidations. So I've already flipped these reactions around from what you'd see in a table of reduction potentials and changed the sign. It's already done. So we can look at these and actually just directly compare. So I actually asked this in a very nice way. So compare Br minus and water as our reactants, both getting oxidized. And when I look, so whichever one's easier, in this case, is also going to be, neither one's positive, so it's whichever one is less negative. And so in this case, I can see that negative 1.07 volts is less negative than negative 1.23 volts. And so in this case, we will produce Br2 still, and it's negative 1.07 volts. And there we go. Cool. And so that's all there is to it. Now, again, you have to have these in front of you and have them handy. And having only the four relevant ones in front of us right where we needed them and having these two that were oxidations already flipped around, I mean, made this job a little easier. But if you just had a big table of all the potentials and stuff like that, you got to find the right reactions. And a couple of them are going to be backwards on a table of reduction potentials. And you'll have to kind of envision them going backwards and changing signs. And it's a pain in the butt. So, but having all the data right here in front of us made this easy. We get Br2 at the anode, we get H2 and hydroxide at the cathode, and we might actually now calculate Ecell as well. So the overall Ecell would just be negative 1.07 and negative 0.83, just adding them together. We've already changed signs and stuff. So, and this just comes out to negative 1.90 volts. And what this means is it's very non-spontaneous, first of all, as we know an electrolytic cell should be, but it also means our power source has to generate a potential of at least positive 1.90 volts to make this reaction happen under standard conditions here. So if your power source isn't up to snuff here, like if it's just I'm just using a AA battery, well, AA batteries are like 1.5 volts. That's not going to be enough. You might have to have a couple of AA batteries in series, which is where you add their volts and it'd be a total of 3 volts instead or something like that. So, but this would be your standard Ecell. It's definitely going to be negative for any electrolytic cell. So, and your power source has to be exactly the positive or more. All right, so quick question. So obviously, let's say, I worked, got a new job as a new chemist here in a plant where they make sodium, and they make sodium by electrolysis. So sodium ions do, but sodium metal doesn't exist in nature. It's so reactive that all of it's been oxidized to Na+. So only Na+ exists in nature, and they make sodium metal by electrolysis. And I see them doing molten electrolysis to make their sodium, like, you guys should really be doing aqueous electrolysis. You wouldn't have to heat it up at all. And they just decide that, yeah, you know what, you really are better off not working here. We'll see you later. You're not hired. We changed our mind. So, and the reason is, sodium is never going to get produced in aqueous electrolysis because for, again, water getting reduced, it's negative 0.83 volts. And negative 2.71 volts, we're not even close. So my question for you is, though, that based on when water gets reduced, it's negative 0.83 volts, what metals could we produce in aqueous electrolysis? Well, we already found out that anything that's more negative than 0.83 volts, like sodium, is not going to work. And so when I look up here, that cutoff is right here. Anything that's more negative than 0.83 volts, like manganese or aluminum, can't make them in aqueous electrolysis. So, but zinc, chromium, iron, cobalt, nickel, hydrogen's not really a metal, but I could do it. Copper or silver, I could totally make those in aqueous electrolysis. Cool. It just had to be less negative or even more positive than negative 0.83 volts, the reduction of water. All right, now we're going to deal with electrolysis calculations, and students often think these are a huge pain in the butt, so hopefully we'll make them a little bit easier here. So first what we're going to do here, at the bottom of the handout there on the study guide, is how many moles of Mn, manganese, will be formed if MnCl2 is electrolyzed for 2 hours using 10 amps. So if you've had second semester physics already or AP physics in high school, it's probably going to be a little bit easier for you, but we're going to try and reason this out as best we can. Now we're doing electrolysis on manganese chloride, and the question's about talking about how much manganese we're going to produce. And so first thing you should figure out is that, we're starting with manganese 2+ in our salt, and we're making manganese metal. And so our half reaction here is manganese 2+ plus 2 electrons goes to manganese. And the big thing you're supposed to see here is that to produce 1 mole of manganese, it takes 2 moles of electrons. So if I wanted to make 2 moles of manganese, it would take 4 moles of electrons, or so on and so forth. If I had 10 moles of electrons, I'd get 5 moles of manganese. It's a 2-to-1 ratio. So all those sorts of things. And so we're going to use a huge effort with some physics knowledge to figure out how many moles of electrons we actually have. And then now knowing this 2-to-1 ratio, we'll figure out how to translate that into moles of manganese. All right, so I've got some simplified equations up here, and we're going to do this without those equations, and then you can decide whether or not you actually want to use one of these simplified equations. All right, so in this question, we're told that it is 10 amps for 2 hours. So if we take those 10 amps, and it turns out an amp is a measure of electrical current. So, and being electrical current is the flow of electrons through our wire here, it is going to be measured in coulombs per second. Recall that coulombs is a measure of charge. And so really this is a measure of some way of quantifying the number of electrons passing through the wire per second. And so 10 amps is 10 coulombs per second. You want to start there. And what we want to do here is that take this number of coulombs per second, if that's what it is for 1 second, then for 2 seconds, it would be 20. For 3 seconds, it would be 30. And what we want to do is multiply by how many seconds we actually run this for to get the total number of coulombs. Once we've got the total number of coulombs, you might recall that Faraday's constant was 96,500 coulombs per mole of electrons. And once we know the total number of coulombs from our calculation over here, we're going to use Faraday's constant to convert it into moles of electrons, because 1 mole of electrons has this many coulombs of charge. So that's kind of the approach we're taking here. So we'll take that 10 coulombs per second. And in this case, we said we're doing electrolysis for 2 hours. Yeah, 2 hours. So 1 hour has 60 minutes. Each minute has 60 seconds. 60 times 60 is 3,600 seconds in an hour. So that's the conversion I'm going to use here. So for 2 hours, that would be 7,200 seconds. Cool. So I did a little math in my head there. So if you notice at this point, we're going to get the total number of coulombs. And to turn that into moles of electrons, I would then take 1 mole of electrons has a total of 96,500 coulombs of charge. And now we'd be able to cancel out the coulombs. And now we've got moles of electrons. And once we got moles of electrons, I can rate that to moles of products just based on stoichiometry here. And so in this case, it takes 2 moles of electrons to get 1 mole of manganese. And that gets us to our final answer here. So moles of electrons cancels, and we'll get the moles of manganese, and let's use our calculator. So we got 10 times 7,200 divided by 96,500 divided by 2. And here we're going to get 0.37 moles of manganese. All right, so we reasoned it out, and I wanted you to see it reasoned out, because ultimately if you can make something make sense to you, it's your best way of storing it in your long-term memory. But we could have also just used this simplified version of the equation here, and it just says take the amps times the time in seconds divided by NF, and it gets you moles of product. So the problem is that nobody's really kind of coined this equation. It's not likely to show up exactly like this in your textbook or anything like that, which means even if your teacher is in the habit of giving you all of the equations and stuff like that, they probably aren't going to give you this one because it's not really an equation. And so as a result, if you want to use this, you kind of have to memorize it. So, and I like to think of like all teachers never fail me or something like that, or this one up here, all teachers A for all, or amps for all teachers must never fail me, or something like that. So, but come up with your own. But if you want to use these two equations, you've got to memorize them, but you can kind of see why it would have worked. We would have just taken the amps, 10 amps right there. We would multiply by the time in seconds, which was 7,200. We would have divided by the number of moles of electrons transferred, 2 right there, just like we divided by 2 there. And then we would divide it by Faraday's constant, just like we did right here. So, and it would have been a very mindless way of calculating this out. And I kind of like mindless. So I wasn't using that in a negative context at all. So cool. But whether you actually reason it out, which again is my personal favorite method. So just because understanding, again, is the key to storing it long term. But if you haven't had second semester physics, this is a pain, and you might just memorize this lovely equation here. Cool. Now, the difference between these top two equations then, if you're going to memorize these, is one gets you moles of products and one gets you the grams of product, the mass of the product. And notice to turn moles into grams, all you do is multiply by the molecular weight. And that's why there's one extra term here. It's still amps times time over NF, but you have to multiply by the molecular weight of your product to convert moles into grams. So if we look at the last question on your handout, it says, how long will it take to plate out 1 kilogram of aluminum from molten AlCl3 with a current of 100 amps? Well, let's get some space here. All right, so we're solving for time. They tell us that we want to get a mass of aluminum of 1.0 kilograms. So, and they said we're using a current of 100 amps. So our current, I is the symbol for current in physics, is 100 amps, 100 coulombs per second. And now the question is really how long? We're solving for time. Now notice they've given us the mass of the product. It's in kilograms, so we'd have to convert it to grams. But essentially we could use this top equation and do some plugging and chugging here. And that's what I'm gonna do. Well, again, we could reason this out, but I think it's just easier to use the equation here. So we're gonna go with 100 amps, which again really is 100 coulombs per second. We'll multiply by the time in seconds, which is what we're going to solve for eventually. Multiply by the molecular weight, and in this case it's the molecular weight of the product. And so they're telling us that we're starting with aluminum chloride, but we're making aluminum. So that's why I made sure to make sure you realize it's the molecular weight of the product and not the reactant. And aluminum has a molar mass of 27 grams per mole. Cool, and then we'll divide by N. And in this case, if we're starting with aluminum AlCl3 there, aluminum is in the +3 oxidation state. And so our half reaction would be Al3 plus 3 electrons going to Al. Cool, and so in this case, the number of moles of electrons transferred is 3. And then times Faraday's constant. Cool, and lo and behold, this is going to equal not 1 kilogram, but 1,000 grams. Cool, and then we can just rearrange and solve for the time in seconds. Let's do that real quick. So in this case, I'm going to take that 1,000 on the product side, multiply by 3, and multiply by 96,500, and then divide it by the 27 times 100. Cool, and in this case, I get 107,000. Time in seconds is 107,222, I think. Yeah, lots of twos. Cool, and obviously that's the time in seconds. If you were doing a multiple choice question, obviously the time could be reported in minutes or hours or days or whatever, and you'd have to do some conversions. But in principle, it comes out in seconds in the equation. So again, these electrolysis, calculations, a little bit of a pain in the butt. For a lot of students, they just prefer memorizing these two. But if you have physics too, I actually would recommend, put just a little bit of effort in to understanding the process to make it make sense. Cool. So if you haven't had the chance yet, hit the subscribe button. And if you want to get notified when I make and release more of these videos. And if you're looking for plenty of practice problems and the study guides and stuff, go to chadsprep.com. Check out my ultimate general chemistry prep course.